Hello everyone, in this video we're going to solve Probability and Statistics 2, Variance 62, May-June 2022. So let's start. Question number 1. A javelin thrower noted the length of a random sample of 50 of a throws. The sample mean was 72.3 and an unbiased estimate of the population variance was 64.3. Find a 92% confidence interval. Okay, so as you can see here, the n is 50, which is more than 30. So although the population distribution is unknown and not stated here, we can assume that the sample distribution is approximately normal since it obeys the central limit theorem. So we can write it as x bar is approximately normal with mu 72.3 and the variance is 64.3, and don't forget to overweight the n, which is 50. Okay, so let's draw a simple sketch. So since this is a confidence interval, meaning it is two-tailed, 0.92, and then here it will be 0.04, 0.04, since the total area is 1. So find the z value and you will get here 1.751, and automatically here will be negative 1.751. So let's find the interval. It will be 72.3, which is the sample mean, plus minus the z value 1.751 multiplied with the standard deviation 64.3 and over 50. So you will get 70.3 and 74.3. Okay, I would like to remind that only the final answer should be 3 significant figures. Throughout the working, it should be exact value and do not do any premature rounding. So question B. A discus thrower wishes to calculate a 92% confidence interval for the population mean length of his throws. He bases his calculation on his first 50 throws in a week. So do you see the problem here? It is not a random sample. Not a random sample. Why? Since it is biased towards the first 50 throws. What about the other than this first 50 throws? It's not a good representative, right? So that's why it is. But the keyword here is that it's not a random sample. So question 2. In the past, the mean height of a plant of a particular species has been 2.3. A random sample of 60 plants was treated with fertilizer and the mean height of these 60 plants was found to be 2.4. So this 2.4 is our test value. Assume that the standard deviation, so it is standard deviation, people, is 0.4. Carry out a test. So okay, the keyword here is carry out a test at a 2.5% significant level of whether the mean height of plants treated with fertilizer is greater than 2.3. So let's write it down. H null. So whenever you carry out a test, you have to write down the H null and H alternative. The keyword here is carry out a test. So when you read this, you write down the H null and H alternative. So the H null is the population mean is 2.3, and the H alternative was suspected to be greater than 2.3, and as you can see, the random sample is 60 plants, so it is more than 30, so it obeys the central limit theorem, so we can assume that it is approximately normal. And 0.4 square, don't forget, because it is 0.4 is standard deviation, right? Over with the n, don't forget. So now let's conduct the test. So before that, let's do a simple sketch. So since it's greater, which means it lies on the right hand side. So 2.5 divided by 100, we get 0.025. And 1 minus 0.025 will be 0.975. So let's find the critical Z value. So the critical Z value will be 1.960. So you read the normal distribution table here. Okay, so we already find the, let me label here, critical Z value. And here is the critical region, because this is a hypothesis testing for a continuous distribution, so it is greater, so anything that lies here will fall into the critical region. So now so our test value was 2.4. Let's standardize this. 2.4 minus 2.3 over the standard deviation should be this, and dumping into the calculator, you will get 1.936. Okay, so as you can see, 1.936 is obviously outside the critical region. So this is, let me label, this is a standardized. You don't have to label this, but I'm just doing it. This also can be called as test statistics. So you have to compare 1.936 is less than 1.960, hence accept H null, reject H alternative, since here anything here will be critical region, and here will be acceptance region. Okay, so yeah, don't forget to write the conclusion. Since you reject the H alternative, there is no sufficient evidence to suggest that the mean height of plants treated with fertilizer is greater than 2.3. So you just copy this one, whether the mean blah blah blah. So yeah, so later I will write there is no sufficient evidence. I denote it as, I abbreviate it as, there is no sufficient evidence. It saves my time to suggest. Never mind, I just write it fully. So question number 3. It is known that 1.8% of children in a certain country have not been vaccinated against measles. A random sample of 200 children in this country is chosen. Use a suitable approximating distribution to find the probability that there are fewer than 3 children in the sample who have not been vaccinated against measles. So every time you do approximating distribution, I will do a simple diagram first. So we have binomial to normal, we also have binomial to Poisson, and we also have Poisson to normal. So each of these has its own criteria that should be fulfilled. So for binomial, in order to transition from binomial distribution to normal distribution, you have to fulfill these two conditions, which is NP more than 5, NQ more than 5. For binomial to Poisson, the NP must be less than 5, and the N must be more than 50. And for this one, the lambda must be more than 15. So another thing is that for this one, continuity correction is compulsory, and this one is a continuity correction is compulsory. Why? This one is discrete, right? Going from discrete to normal. Going from discrete to normal. Both of these continuity correction is mandatory. But for this one, you're going from discrete to discrete. So there's no need for continuity correction here. So let's see for this question which approximation we have to use. So this is binomial, n is 200 and the probability of success is 1.8%. I write it as decimal. You just 1.8 divided by 100, you will get 0.018. Okay, so the n is 200, which is more than 50, right? And 0.018. So let's find the NP. 200, or the P equation is justified. So we can do this one first. So n is 200, it is more than 50, and P is, let me calculate, you will get 3.6. 3.6 is less than 5. Okay, so the lambda will be 3.6. So the question one, fewer than 3 children, probability x less than 3, which means 3 is not inclusive, so probability x 0, 1 and 2. So lambda e to the power of negative lambda 1 plus 3.6 plus 3.6. Wait, let me write 6, 12, 2 factorial. So dumping into the calculator, and 3, you get 0.303, which is 3 significant figures. Okay, so question number 4. The number of cars arriving at a certain road junction on a weekday morning has a Poisson distribution between 4.6 per minute. So this one, 4.6, the interval is per minute. So when you're dealing with Poisson distribution type of question, it's really important to take note of the interval, whether per minute, half an hour, or per hour, or per year, per month. Okay. Traffic lights are installed at the junction, and a council officer wishes to test at the 2% significant levels whether there are now fewer cars arriving. Okay, so this fewer cars arriving is the alternative hypothesis. He notes the number of cars arriving during a randomly chosen 2-minute period. So look at here, 2-minute period. So the lambda now, so the interval now is 2-minute period. So 4.6 is per minute. What about 2 minutes? You just take the 4.6 multiply by 2, you will get 9.2. So the H now is that the lambda is 9.2, and the alternative hypothesis is the lambda is fewer. It was suspected to be fewer than the 9.2. So we have to find the critical region for the test. Okay, critical region is also known as rejection region. So since it's less than, so probability, since the alternative is less, the symbol here, so our critical region, and the significant level is 2 divided by 100 is 0.02. So you have to find the value of C that obeys this, that gives us less than 0.02 the probability. So basically type an error. So let's try P, let's try at most 3. So dump into the calculator. Wait, let me write down this one first. Sorry, it's 9.2. So dump into the calculator, you will get 0.0184, which is less than 0.02, right? But if you make a simple sketch like this, 0 1 2 3 4 5 6, at the end we don't know the end. So if less than 3, if at most 3, you get 0.0184. But could it be at most 4? Let's try. Probability x at most 4. So you just take the previous one and then just plus with this one. So and you will get 0.0486, which is greater than 0.2. So it is correct that x at most 3 is our critical region. So you have to compare this. So this working is needed, okay, to show that x at most 3 is the critical region. Okay. So question C. The officer notes that during a randomly chosen 2-minute period, okay, still 2-minute period, on a weekday morning, exactly 5 cars. So 5 is not within the critical region, right? 5 is not in the critical region, which means the H0 is not rejected, but it is instead accepted. Accept H0, reject H alternative. Since it doesn't fall in the critical region, that means it falls in the acceptance region. So write the conclusion. There is no sufficient evidence to suggest that there are fewer cars arriving. Okay, question D. State with the reason whether it's possible that type 1 error. Okay, what is type 1 error? So type 1 error means reject through H0, but we didn't reject H0, right? We accept H0, so no, since H0 was accepted. Okay. So question C. The number of cars arriving at another junction. Okay, another junction. 4.6 per minute. Per minute. Okay, use a suitable approximating distribution. Wait, let me take our diagram just now. It's better if you could memorize this one, because you will use it frequently. Change the color. Okay. In an hour, more than 300 approximation. Okay. So let's change the lambda. So 4.6, you just multiply by 60, you will get 276. So you have to find the probability x more than 300, but be careful. As I stated here, we're going from Poisson to normal, because the lambda is 276, which is way bigger than 15. So yeah, it fulfills the condition. Another thing is that you have to do continuity correction, since you're going from discrete to normal distribution. So I usually do like this. You could do like this as well. (299, 300, 301). So more than 300 means 300 not inclusive. So So you just take this one, this 300.5. So probability x greater than 300.5. So let's standardize it. 300.5 minus 276 over 276. Oh, I forgot to write just now. This one becomes 276. Okay, this one will give you mark because in the Poisson, if you don't remember, lambda for Poisson only, lambda is equal to variance and also equals to the mu. So pressing this into the calculator, you will get 1.475, 3 decimal places because you're going to read in the table. And let's do a simple sketch. That's very bad. So 1.475 is here. So 1 minus this area, which you read at the table later, you get 0.92, 1 minus 0.9299, and then you will get 0.0701, 3 significant figures. That's the final answer. Only the final answer is in 3 significant figures. Throughout the working, exact value. So question number 5. A random variable x has probability density function, given by blah blah blah. Show that expectation is 11 over 4. So let me write down the formula here. For probability density function, the expectation is all the x, fx dx, and for variance, all x squared fx dx minus with mu squared. The difference is that this one the function multiplied by x, this one the function multiplied by x squared, and you have another extra one, you have to minus the mu squared. Okay, so let's integrate it. Integration from 2 to 4, all x here means the entire interval, entire domain stated, okay, which is 2 to 4. You bring the constant to the front, 3 over 16, and then okay, I expand it first to make our integration a lot easier. We got 4x squared minus x cubed. Okay, I forgot dx. Okay, so you integrate, we get 4x cubed over that one, and then this one like this. So substituting into the calculator, you will get 2.75, which is similar as 11 over 4. So question B, find variance x. So use this formula I write it just now, this one. This like this. Now bring the constant to the front. And the mu just now was 2.75 squared. Okay. So let's expand it just like this. Now 4x cubed minus x to the power 4 dx. Don't forget the dx. In this case it is dx because the domain is given in terms of x, right? And our function is also f of x. So let's integrate it. Of course you can simplify if you want. So press into the calculator and then you will get 19 over 18. If you write it in 3 significant figures as well, but fractions are much more safer because you may use it in the next question. So question C, okay. Given that the median of x is m, find this one. So to solve this question, it is a good idea to do a simple sketch. You can do a simple sketch or accurate one, it's up to you, because you won't get any mark for it, but it's just for you to visualize what's happening. So our fx was negative 3 over 16 x squared plus 3 over 4x. So it's quadratic and the coefficient of x squared is negative 3 over 16, which means it has this shape. However, our domain is only defined from 2 to 4. Which means I have to erase this one. This is 2, this is 4. Okay. So let's say 3 is here. Since we have to find, since m is less than 3, so let's say m is here, so you have to find this area basically. So what can you do is you can take this entire area and then minus with this segment here. So how to do that? So let's write it down mathematically first. Probability x less than 3 minus the probability x less than m. So let's integrate from 2 to 3, the constant to the front as usual. Yes. Okay, probability x less than m is 0.5. You should know this. Okay. So you integrate. And you solve this, you will get 0.188. Okay, that's the answer. Let me check. Yeah, 3 significant figures. Okay. So question number 6. The masses in kilogram of large and small saccade, blah blah blah. Okay, let's denote this one as L and this one as S. And L distributed normally, 3, 11, S distributed normally, 14, 3. Find the probability that the mass of randomly chosen large sac is greater than 4 times. So it's a multiple here. So it will be like this. And we can write it like this. So we have to find this one. You can denote this one as M or any letter that you want, if you feel it lengthy to write, but I just write it like this. It's up to you. So now let's find the distribution of L minus 4S. So the expectation or the mean will be 53 minus 4 times 14, and the variance will be, okay, remember variance are always added, so 11 plus the constant should be squared, so it becomes 4 squared and times by 3. So we get here negative 3 and then here 59. So we just write it here. Okay. Okay. Now let's find the probability. 0 minus negative 3 over the standard deviation. Pressing into the calculator, you will get 0.391. Let's do a simple sketch as usual. So 1 minus 0.6521, and the final answer you will get 0.348, three significant figures. So question B, a leaf can safely carry a maximum mass of 1000 kg. Find the probability that a leaf can safely carry 12 randomly chosen large sacks and 25 randomly chosen small sacks. So now it is total. So basically let's denote total distributed normally. So basically what you're finding is L1 plus L2 plus L3 L4 blah 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 until L12. And similar for that one. For small set, S1 plus S2 plus S3 plus blah 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 until S25. So the mean will be just 53. We can just times by 12, or you can do it manually if you want. Plus 14 times 25, you will get 986, and the variance you will get 11 times 12 plus 25 times 3, you will get 207. So I'm going to find, since it should be safer, it should be like this, 1000. Let's standardize it. 1000 minus 986 over the standard deviation. Pressing into the calculator will give you 0.973. Do a simple sketch so that you won't make a mistake. So sorry, I made a mistake. My diagram previous was erroneous. It is less than right. 0.973. So in this case, no need 1 minus anything, just 0. Direct 0.8348, 0.8. Okay. So done with this question. So question 7. X is a random variable with distribution. Okay, X, our axis distributed Poisson. A random sample of 100 values of X is taken. Find the probability that the sample mean is less than 2.8. So since our random sample here is 100, and it obeys the central limit theorem, so our population distribution here is, we know, it is Poisson, but it is not normal. However, since it obeys the central limit theorem, the sample distribution is approximately normal. So here is 2.90, since the lambda is same as the mu and also same as the variance. 2.90, however, you have to over with the 100. So probability X bar less than 2.88. 2.88 minus 2.90 over the standard deviation, 2.90, 100. Sorry. You will get negative 0.1174. Negative 0.117 is sufficient because you're reading into the table, right? So 1 minus 0.5466, and the final answer 0.443, and 3 significant figures. So that's all for this question. See you next video, and don't forget to like and subscribe this video. Thank you for watching.